Okay, we're back with 6.4, growth and decay, and we're looking at half-life of radioactive substance with a constant. So in this case, we have the definition of half-life, where half-life is ln of 2 over k. And we look at this first problem where we're choosing a base becomes at issue here. And we have our options when we're choosing base. We don't have to pick base E, 1/2, or anything. We look at the data, and sometimes it's helpful to pick a base that's compatible with the numbers that we're dealing with. So let's read through the problem, and then I'll do another checklist as we go through. At the beginning of the summer, the population of a hive of bulb-faced hornets, which are actually wasps, number one, is growing at a rate proportional to the population. So that tells you that it's an exponential growth rate. From a population of 10 on May 1st, to the number of hornets grows to 50 in 30 days. So if the growth rate of the population continues to follow the same model, how many days after May 1st will the population reach 100? So again, we start off with our dy dt is equal to negative kt. That's our exponential growth and decay formula. And we know that it's going upward, okay? So now we start off with our equation. Y is equal to y sub 0. And there's a base b to the ht that we're using. Now, what I'm going to do is I'm going to say, looking at the data, when t is equal to 0, y sub 0 is equal to 10. And then when t is equal to 30, y is equal to 50. So I noted that they are from y sub 0 to the next y value, it multiplies by 5. So I'm going to go ahead and use base 5 for this, okay? So in the second step where I have the equation, you note that I just put the y is equal to 10 because 10 is the initial population, and then 5 to the ht power. So then if I'm going to use base 5, you can see I put 50 in then, because now I'm going to use the 50 and the 30 because I want to find out what h is. So in order to do that, I plug in the other data, and you can see I divide by 10, and I get 5 to the first on the left is equal to 5 to the 30h. So 1 in this step is equal to 30h. H is equal to 1 over 30. So then if I come over here, then I have this equation, the equation with a star by it. Y is equal to 10 times 5 to the 10 over 30 power. Then what we want to do here is we want to know if the growth of the population continues to follow the same model, how many days after May 1st will the population reach 100? So if you look, now in step 3, I'm going to make my population equal to 100. And then after that, I go through the process of solving for t. It turns out I get t is equal to 42.920 days. So, and that will be the answer to the question. In 42.920 days, the population will reach 100. So that is the answer to that question. You can see that we didn't have to use a base E. We didn't have to use, we chose to use 5 as the base because it made our computations easier. Okay. Then we have a carbon-14 dating where scientists, in example 5 now, scientists who use carbon-14 dating use 5,700 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei present have decayed. So again, we're talking about a decay equation. And with that, we're going to use A of t is equal to A sub 0, B for the base, to the t over k. Now, the reason why I'm going to use that will become evident as we talk about using values of 1/2 to the first power, 1/2 to the second power with our number of years. So the k value is 5,700. A of t is the amount of time the amount present. In this case, we're the amount of a radioactive nuclei, the amount at time t, and then the base I'm going to use is the half-life base, 1/2. It just makes it a little bit easier dealing with half-lives. And then we want to know find the age of the sample in which 10% of the radioactive nuclei originally present has decayed. So then that means that 90% remains, or 0.9 a sub 0. So when we work this out, you can see that here's my equation. I plugged in my K value and my 1/2 for the base. And then I say 90% of my original is equal to the original times 1/2 to the T over 5700. So then I get divide both sides, divide out the a sub 0. And so I get 0.9 is equal to 0.5 to the T over 5700. And then at that point, I have to solve for T because the question says, find the age of a sample. So I'm going to take the ln of both sides. And it turns out I get T is equal to 5700 ln of 0.9 over ln of 0.5, or I get T is approximately 866 years old. Okay, so that answers that question. Okay, that would be the age of the sample in which 10% originally present has decayed. Okay, that's it for that, using carbon-14. Example 6, using Newton's law of cooling then. So in Newton's law of cooling, we have a new formula because think of when something cools, it cools, such as a cup of coffee that's on the counter, it'll cool until it gets to the temperature of the surrounding room. And it doesn't keep going down further than that because it just kind of hits what we call equilibrium. So with Newton's law of cooling, in this case, we have a hard-boiled egg at 98 degrees Celsius. That's going to be our temperature initial. I have T sub 0, is put into a pan under running water, 18 degrees Celsius. And that's the temperature of the surrounding water. And it's to cool. After 5 minutes, the egg's temperature is found to be 38 degrees Celsius. How much longer will it take the egg to reach 20 degrees Celsius? And what time is it when the egg is at 20 degrees Celsius? So that's what that's really asking. How much longer will it take? Well, what time? We've got to find out what time. And then we'll have to figure out how much more time we need. So here's Newton's law of cooling, where we have the differential equation is d of the temperature, capital T, dt is equal to negative K times the quantity, the temperature, minus the temperature surrounding. So I have them listed over here. Capital T, temperature of an object, and T sub S is temperature of the surrounding environment, and T sub 0 is the initial temperature of an object. Okay, and you have some information if you're just trying to think about, if you have 98 degrees Celsius, you're thinking about, oh, what is that? And we're used to dealing with Fahrenheit. So 208.4 degrees Fahrenheit is 98. So 212 degrees Fahrenheit is boiling temperature, just in case you're wondering if that was very hot. And it certainly was. So here's what we do. We start out with our function, and we have our formula, and think about the ordered pairs as being lowercase t, capital T. So we plug in our known quantities where T of the surrounding is 18, T initial is 98 degrees, the hard-boiled egg, and then T of the surrounding goes here as well, okay, and e to the negative kt. So when we solve for T, this is our equation that we get. So then when we manipulate this and we say, okay, we know that the temperature is 38 degrees. It says that after 5 minutes, the temperature's egg is found to be 38 degrees. So we plug in the 5 for the time, 5 minutes, and then the 38 degrees. Solving for K, then we get 20 over 80. Then we subtract 18, we get 20. 20 divided by 80, we get 1/4 is equal to e to the negative 5k. And then solving for k, we get ln of 4 over 5. Okay, so we have our k value. And now we're going to put that in our equation. So we're going back to our general solution. Here's our general solution. And then we've got to put our constant in for our e to the negative kt here. We've got our k in there. And then we know also that the temperature is, we want to know how much longer will it take for the egg to reach 20 degrees Celsius? So we force the temperature to be equal to 20. Solving for that, it turns out we get a time of 13.3 minutes. So we know that it'll take 13.3 minutes for it to go from the initial temperature all the way up to 20 degrees down. So we just want to know how much longer will it take. So it took 5 minutes to get to 38. So it would be 13.3 minus those 5 minutes. So the answer for this problem is in 8.3 minutes. Okay. And one of the things that you can do with the calculator is you can plug it in and you can say y sub 1 is 20 and y sub 2, because remember that'll be 20, the temperature will be 20. And then y sub 2 then will be 80 e to the negative ln of 4 over 5x plus 18. And you can see that they meet at that point where you have your y is equal to 20 and then your function y sub 2 as your exponential function, and second calc 5, or second trace 5 for intersection. You can find the point is 13.320. Okay. And then there's a little thing about J. Ernest Wilkins. He was a mathematician. By the age of 19, J. Ernest Wilkins had earned a PhD degree in mathematics from the University of Chicago. He then taught, served on the Manhattan Project, the goal which was to build the first atomic bomb, and worked as a mathematician and physicist for several corporations. In 1970, Dr. Wilkins joined the faculty at Howard University and served as head of the electrical engineering, physics, chemistry, and mathematics department before retiring. He was also the distinguished professor of applied mathematics and mathematical physics at Clark Atlanta. Worked a lot with growth and decay and differential equations. Brilliant man. So anyhow, that's it for 6.4, and we'll pick up in class with going over any questions you might have on the homework. And this is Alanator on video 2 out.